Hello, welcome to the video lecture series on digital image processing. In our last lecture, we had talked about a number of basic transformations, and we have said that these transformations are very useful to understand the image formation process. So, in the last class, what we had talked about is the basic transformations, and we have talked about the transformations like translation, rotation and scaling, and these transformations we have said both in the 2-dimension and 3-dimensional cases. Then for all these transformations, we have also seen what is the corresponding inverse transformation. Then after that, we have gone for the conversion from the Cartesian coordinate system to homogeneous coordinate system, and we have seen the use of homogeneous coordinate system in perspective transformation, where perspective transformation we have said is an approximation of the imaging process. So, that when a camera takes the image of a point in a 3-dimensional world, then this imaging transformation can be approximated by the perspective transformation that we have discussed in the last class. Today, we will talk about the inverse perspective transformation. We have said that the perspective transformation takes an image of a point or a set of points in the 3-dimensional world, and these points are mapped to the imaging plane, which is a 2-dimensional plane. The inverse perspective transformation just does the reverse process, that is, given a point in the imaging plane, we will see that using this inverse perspective transformation, whether it is possible to find out that what is the point in the 3-dimensional coordinate system to which this particular image point corresponds. Then we will also talk about the imaging geometry, where the world coordinate system and the camera coordinate system are not aligned. You try to remember that in the last class, the imaging geometry that we had considered, there we have assumed that the 3-dimensional world coordinate system is aligned with the camera coordinate system. That is, x axis of the camera is aligned with the x axis of the 3D world, y axis of the camera is aligned with the y axis of the 3D world, and z axis of the camera is also aligned with the z axis of the 3D world. In addition to that, the origin of the camera coordinate system also coincides with the origin of the image coordinate system. In today's lecture, we will take a generalized imaging model, where the camera coordinate system and the 3D world coordinate system, they are not aligned, and which is a general situation. Then we will try to see that what are the transformations which are involved in such a generalized imaging setup, which will help us to understand the image formation process in a generalized setup. Then we will illustrate this concept with the help of an example. Now, let us briefly recapitulate what we had done in the last class. Now, this figure shows the imaging geometry that we had considered, where the 3D world coordinate system is aligned with the camera coordinate system. There we have taken a 3D point whose coordinates are given by x, y, z, all in the capital, and x, y lowercase coordinates are the corresponding image point in the imaging plane. And we have assumed that the focal length of the camera is lambda. That means, the coordinate of the focal point of the lens center is 0, 0, lambda. Now, using this particular figure, we have tried to find out a relation between the 3D world coordinate x, y, z and the corresponding image point, which is x, y. For that, what we have done is, we have taken a conversion from the Cartesian coordinate system to a homogeneous coordinate system. So, while doing this conversion, what we have done is, every component of the coordinate, that is x, y, z, is multiplied by a non-zero arbitrary constant k, and the same value of k is appended with the 3 components. So, in the for a Cartesian coordinate x, y, z, the corresponding homogeneous coordinate is given by kx, ky, kz and z. So, for a world coordinate point x, y, z, once we have the corresponding homogeneous coordinate kx, ky, kz and k, then we found that after this conversion, if we define a perspective transformation, so this perspective transformation matrix P, which in this case is 1 0 0 0, 0 1 0 0, 0 0 1 0 and 0 0 minus 1 upon lambda 1, and the homogeneous coordinate W h is transformed with this perspective transformation matrix P, then what we get is the homogeneous coordinate of the camera point to which this world point W will be mapped, and the homogeneous coordinate of the camera point of the image point after the perspective transformation is obtained as kx, ky, kz minus k z by lambda plus k. And you will see that if I convert this homogeneous camera point, the homogeneous image point into the corresponding Cartesian coordinate, then this conversion gives us the Cartesian coordinates of the image point as x, y, z equal to lambda x divided by lambda minus z, lambda y divided by lambda minus z and lambda z divided by lambda minus z. So, you just note that x, y, z in the lowercase letters, these indicate the camera coordinate, the image coordinate, whereas x, y, z in the capital form, this represents the coordinate in the 3D world of or the 3D coordinate of the world point W. Now, what we are interested in is the camera coordinate x and y. At this moment, we are not interested in the image coordinate z. So, this can be obtained by simple conversion, that if we find out the value of lowercase z with respect to lambda and capital Z, then after solving the same equations, here, that is lowercase x, lowercase y and lowercase z, we find that the image coordinate x and y in terms of the 3D coordinate capital X and capital Z is given by x equal to lambda x divided by lambda minus capital Z, and image coordinate y equal to lambda times capital Z divided by lambda minus capital Z. So, as we said that the other value, that is the z coordinate in the image plane, is of no importance at this particular moment, but we will see later that when we talk about the inverse perspective transformation, when we try to map an image point to the corresponding 3D point in the 3D world, then we will make use of this particular coordinate z in the image plane as a free variable. So, now let us see that what is the corresponding inverse perspective transformation that we can have. So, as we have said that a perspective transformation maps a 3D point onto a point in the image plane. The purpose of inverse perspective transformation is just the reverse. That is, given a point in the image plane, the inverse perspective transformation or P inverse tries to find out the corresponding 3D point in the 3D world. So, for doing that, again we make use of the homogeneous coordinate system, that is the camera coordinate C or the image coordinate point C will be replaced, will be converted to the corresponding homogeneous form, which is given by C h, and the world coordinate, world point W will also be obtained in the homogeneous coordinate form WH. And we define a inverse perspective transformation P inverse, which is given by 1 0 0 0, 0 1 0 0, 0 0 1 0 and 0 0 1 upon lambda 1. And you can easily verify that this matrix, this transformation matrix is really an inverse of the perspective transformation matrix P, because if we multiply the perspective transformation matrix by this matrix P inverse, what we get is really an unitary matrix. Now, given this inverse perspective transformation matrix, as we said that if we assume an image point say x naught y naught, and we want to find out what is the corresponding 3D world point W to which this x naught y naught image point corresponds. So, the first step that we will do is to convert this image point x naught y naught to the corresponding homogeneous coordinate, which will be obtained as k x naught, k y naught and 0, and then the fourth component comes as k. Now, here you find that the third component or z coordinate we have taken as 0, because what we have is a point in 2 dimension, that is on the imaging plane. So, we have assumed the z coordinate to be 0. Now, if we multiply or if we transform this homogeneous coordinate kx naught, ky naught, 0 k with the inverse perspective transformation P inverse, then what we get is the homogeneous coordinate corresponding to the 3D world point, which is obtained as WH as given in this equation. WH is equal to kx naught, ky naught, 0 k. Now, from this homogeneous coordinate system, if I convert this to the Cartesian coordinate form, then the Cartesian coordinate corresponding to this homogeneous coordinate is obtained as W equal to capital X, capital Y, capital Z, which is nothing but x naught, y naught, 0. So, you find that in this particular case, the 3D world coordinate is coming as x naught, y naught, 0, which is the same point from where we have started, that is the image point from where we have started. Moreover, for all the 3D coordinate points, the z component always comes as 0. Obviously, this solution is not acceptable, because for every coordinate or for every point in the 3-dimensional world, the z coordinate cannot be 0. So, what is the problem here? If you remember the figure of imaging system that we have used, let me just redraw this particular figure. We had an imaging plane, xy plane like this, on which the camera coordinate system and the image coordinate system, camera coordinate system and the 3D world 3D coordinate system, they are perfectly aligned. So, we had this x same as capital X, we had this y same as capital Y, we had this z same as capital Z, and this is the origin of both the coordinate systems, and we had somewhere here the optical center of the lens. Now, if I take some point here, some image point here, and if I draw a line passing through this image point and the camera optical center, and the world point W comes somewhere at this location. So, we have seen in the previous figures that this point, if I call this point as C, this point C is the image point corresponding to this 3D world point W, whose coordinate is given by capital X, capital Y, capital Z, and this C in our case has a coordinate of x naught, y naught and 0. And when we have tried to map it back, this point C, to the 3D world coordinate system, what we have got is for every point W, the value of Z came out to be 0. Now, the problem that comes here is because of the fact that if I analyze this particular mapping, that is mapping of point W in the 3D world to point C in the image plane, this mapping is not a one-to-one mapping, rather it is a many-to-one mapping. So, for example, if I take any point on this particular straight line passing through the point C and the point 0 0 lambda, which is nothing but the optical center of the camera lens, then all these points on this line will be mapped to the same point C in the image plane. So, naturally, this being a many-to-one mapping, when I do the inverse transformation using the inverse perspective transformation matrix from image point C to the corresponding 3D world, the solution that I will get cannot be acceptable solution. So, we have to have something more in this formulation, and let us see what is that we can add over here. Now, here if I try to find out the equation of the straight line which passes through the point x naught y naught, that is the image point, and the point 0 0 lambda, that is the optical center of the camera lens, the equation of the straight line will come of this form, that is capital X equal to x naught by lambda into lambda minus capital Z, and y equal to capital Y equal to y naught by lambda into lambda minus capital Z. So, this is the equation of the straight line. So, that the points, every point in this straight line is mapped to the same point x naught y naught in the image plane. So, the inverse perspective transformation, as we have said, that it cannot give you a unique point in the 3D world, because the mapping, the perspective transformation was not an one-to-one mapping. So, by using the inverse perspective transformation, even if we can't get exactly the 3D point, but at least the inverse transformation matrix should be able to tell me that the points belonging to which particular line maps to this point x naught y naught in the image plane. So, let us see whether we can have this information at least. So, for doing this, in earlier case, when we have converted the image point x naught y naught to the homogeneous coordinate, then we have taken k x naught, k y naught, 0 and k. Now, here the z coordinate, what we will do is, instead of assuming the z coordinate to be 0, we will assume the z coordinate to be a free variable. So, in our homogeneous coordinate, we will assume the homogeneous coordinate to be k x naught, k y naught, k z and k. Now, this point, when it is inverse transformed using the inverse transformation matrix, then what we get is the world coordinate, the world point in homogeneous coordinate system as W h is equal to P inverse C h, and in this particular case you find that this W h is obtained as k x naught, k y naught, k z, k z by lambda plus k. So, this W h we have got in the homogeneous coordinate system. Now, what we have to do is, this homogeneous coordinate we have to convert to the Cartesian coordinate system, and as we have said earlier that for this conversion we have to divide all the components with the last component. So, in this case k x naught, k y naught and k z, all of them will be divided by k z by lambda plus k. So, after doing this division operation, what I get in the Cartesian coordinate system is W equal to, sorry, here it is not C, it should be W. So, W equal to x y z, which is equal to, so this point should be W. So, what we get is W equal to x y z, which is equal to lambda x naught divided by lambda plus z, lambda y naught divided by lambda plus z and lambda z divided by lambda plus z. So, on the right hand side all the z's are the lowercase letters, which is the free variable that we have assumed, that we have used for the image coordinate. And for the matrix, the column matrix on the left hand side, all x, y, z are in the uppercase letters, which indicates that these x, y, z are the 3D coordinate. So, now what we do is, we try to solve the values, solve for the values of capital X and capital Y. So, just from this previous matrix, you find that the capital X is given by lambda x naught divided by lambda plus lowercase z, capital Y is given by lambda y naught divided by lambda plus lowercase z, and capital Z is equal to lambda lowercase z divided by lambda plus lowercase z. So, from these three equations, I can obtain capital X equal to x naught by lambda into lambda minus z, and capital Y equal to y naught by lambda into lambda minus z. So, if you recall the equation of the straight line that passes through x naught, y naught and 0, 0 lambda, you find that the equation of the straight line was exactly this, that is capital X equal to x naught by lambda into lambda minus z, capital Z, and capital Y equal to y naught by lambda into lambda minus capital Z. So, by using this inverse perspective transformation, we have not been able to identify the 3D world point, which is of course not possible, but we have been able to identify the equation of the straight line, so that the points on this straight line maps to the image point x naught, y naught in the image plane. And now, if I want to exactly find out a particular 3D point to which this image point x naught, y naught corresponds, then I need some more information. So, for example, I at least need to know what is the z coordinate value of the particular 3D point w. And once we know this, then using the perspective transformation along with this information of the z coordinate value, we can exactly identify the point w which maps to point x naught, y naught in the image plane. Now, till now all the discussions that we have done, for all these discussions we have assumed that the image coordinate system and the camera coordinate system, they are perfectly aligned. Now, let us discuss about a general situation where the image coordinate system and the camera coordinate system, they are not perfectly aligned. So, here we assume that the camera is mounted on a gimbal. So, if you mount the camera on a gimbal, then using the gimbal, the camera can be given a pan of angle theta. It can also be given a tilt by an angle alpha. So, you remember that pan is the rotation around z axis and the tilt is rotation around x axis. We also assume that the gimbal center is displaced from the 3D world coordinate origin 0, 0, 0 by a vector w naught, which is equal to x naught, y naught, z naught. And finally, we also assume that the camera center or the center of the imaging plane is displaced from the gimbal center by a vector r, which will have components say r1, r2 and r3 in the x, y and z direction of the 3D world coordinate system. Now, here our interest is, given such a type of imaging arrangement, now if we have a 3D world a point in the 3D world coordinate w, what will be the camera coordinate, what will be the image point C to which this world point w will be mapped. So, this is a general situation, and now let us see that how we can obtain the solution to this particular problem, that for this generalized imaging setup for a world point w, what will be the corresponding image point C. So, the steps will be like this. Since our earlier formulations were very simple, in which case we have assumed that both the camera coordinate system and the 3D world coordinate system, they are perfectly aligned. In this generalized situation, we will also try to find out a set of transformations which, if applied one after another, will bring the camera coordinate system and the world coordinate system in perfect alignment. So, once that alignment is made, then we can apply the perspective transformation to the transformed 3D world points, and this perspective transformation to the transformed 3D world points give us the corresponding image coordinate of the transformed point W. So, what are the transformation steps that we need in this particular case? So, the first step is we assume that the image coordinate system and the 3D world coordinate system, they are perfectly aligned. So, from this we displace the gimbal center from the origin by the vector W naught, and after displacing the gimbal center from the origin by W naught, we pan along x axis by an angle theta, followed by tilt around tilt of z axis by angle alpha, which will be followed by the final displacement of the image plane with respect to gimbal center by the vector r. So, we have 4 different transformation steps which are to be applied one after another, and these transformation steps will give you the transformed coordinate of the 3D world point W. So, let us see how this transformation is to be applied one after another. So, here on the left hand side we have shown a figure where the camera coordinate system and the world coordinate system are perfectly aligned. Now, from this alignment, if we give a displacement by a vector W naught to the gimbal center, then the camera will be displaced as shown on the right hand side of the figure, where you find that the center is displaced by vector W naught. You remember that if I displace the camera center by vector W naught, then all the world coordinates, all the world points will be displaced by a vector minus W naught with respect to the camera. Now, you just recollect that when we try to find out the image point of a 3D world point, then the image point, the location of the image point is decided by the location of the 3D world point with respect to the camera coordinate. It is not with respect to the 3D world coordinate. So, in this case also, after a set of transformations, we have to find out what are the coordinates of the 3D world point with respect to the camera coordinate system, where originally the coordinates of the 3D world point are specified with respect to the 3D world coordinate systems. So, here as we displace the camera center by vector W naught, so all the world coordinate points, all the world points will be displaced by the vector which is negative of W naught, that is by minus W naught. And if W naught has components of x naught along x direction, y naught along y direction and z naught along z direction, so the corresponding transformation to the 3D points will be minus x naught, minus y naught and minus z naught. And we have seen earlier that if a 3D point is to be displaced by minus x naught, minus y naught, minus z naught, then in the unified representation, the corresponding transformation matrix for this translation is given by G equal to 1 0 0 minus x naught, 0 1 0 minus y naught, 0 0 1 minus z naught and then 0 0 0 1. So, this is a transformation matrix which translates all the world coordinates, all the world points by vector minus x naught, minus y naught, minus z naught, and this transformation is now with respect to the camera coordinate system. The next operation, as we said, that after this displacement we pan the camera by angle theta, and this panning is done along the z axis. So, when we pan along z axis, the coordinates which are going to change is the x coordinate and the y coordinate. The z coordinate value is not going to change at all. And for this panning by an angle theta, again we have seen earlier that the corresponding transformation matrix for rotation theta is given by r theta equal to cosine theta sin theta 0 0 minus sin theta cosine theta 0 0, then 0 0 1 0 and then 0 0 0 1. So, when we rotate the camera by an angle theta, all the world coordinate points, will be rotated by the same angle theta, but in the opposite direction and the corresponding transformation matrix will be given by this matrix r theta. So, we have completed two steps, that is first displacement of the camera center with respect to origin of the world coordinate system, then panning the camera by angle theta. The third step is, now we have to tilt the camera by an angle alpha, and again we have to find out what is the corresponding transformation matrix for this tilt operation, which has to be applied to all the 3D points. So, for this tilt operation by an angle alpha, the corresponding transformation matrix R alpha will be given by 1 0 0 0, 0 cosine alpha sin alpha 0, then 0 minus sin alpha cosine alpha 0 and 0 0 0 1. So, you just recollect that these are the basic transformations which we have already discussed in the previous class, and how these transformations are being used to understand the imaging process. So far we have applied one displacement and two rotation transformations along r theta and r alpha. Now, find that this r theta and r alpha, they can be combined into a single rotation matrix R, which is equal to r alpha concatenated with r theta, and the corresponding transformation matrix R will be given by cosine theta sin theta 0 0, then minus sin theta cosine alpha sin alpha 0, then sin theta sin alpha minus cosine theta sin alpha, then cosine alpha 0 and then 0 0 0 1. Then final transformation that we have to give to the camera center or the center of the imaging plane from the gimbal center by a vector r, and this vector r has the components r1, r2 and r3 along x, y and z directions. And by this transformation, now all the world points are to be transformed or to be translated by a vector minus r1, minus r2, minus r3. And the corresponding translation matrix now will be T equal to 1 0 0 minus 1, 0 1 0 minus r2, 0 0 1 minus r3 and then 0 0 0 1. So, if I apply all these transformations one after another and I represent the 3D world point W by the corresponding homogeneous coordinates W h, then you find that these transformations T, R and G taken together on this homogeneous coordinate W h gives you the homogeneous transformed point W as seen by the camera. And once I have this transformed 3D points, then simply applying the perspective transformation on these transformed 3D points will give you the camera coordinate in the homogeneous form. So, now the camera coordinate C h is given by P T R G into W h. So, you remember that this coordinate comes in the homogeneous form. Then final operation that you have to do is to convert this homogeneous coordinate C h into the corresponding Cartesian coordinates C. So, that Cartesian coordinate, if I solve those equations, will come in this form. You can try to derive these equations, that x equal to lambda into x minus x naught cosine theta plus y minus y naught sin theta minus r 1 divided by minus x minus y x naught sin theta sin alpha plus y minus y naught cosine theta sin alpha minus z naught cosine alpha plus r 3 plus lambda, and the image coordinate y is given by lambda x minus x naught sin theta cosine alpha plus y minus y naught cosine theta cosine alpha plus z naught sin alpha minus r 2 divided by minus x naught sin theta sin alpha plus y naught cosine theta sin alpha minus z naught cosine alpha plus r 3 plus lambda. So, these are the various transformation steps that we have to apply if I have a generalized imaging setup, in which case the 3D coordinate axis and the camera coordinate axis, they are not aligned. So, the steps that we have to follow is, first we assume that the camera coordinate axis and the 3D coordinate axis, they are perfectly aligned. Then give a set of transformations to the camera to bring to its given setup and apply the corresponding transformations, but in the reverse direction to the 3D world coordinate points. So, by applying these transformations to the 3D world coordinate points, the image points, the 3D world coordinate points as seen by the camera will be obtained in the transformed form. And after that, if I apply the simple perspective transformation to these transformed 3D points, what I get is the image point corresponding to those transformed 3D world points. Now, let us try to see an example to illustrate this operation. So, let us take a figure where we assume that the camera or the center of the imaging plane of the camera is located at location 0, 0, 1 with respect to the 3D world coordinate system x, y, z. And we have an object placed in the x, y plane, where one of the corners of the object is at location 1, 1, 0, 2, 0.2, and we want to find out that what will be the image coordinate for this particular 3D world point, which is now a corner of this object as placed in this figure. So, what we will try to do is, we will try to apply the set of transformations to the camera plane one after another and try to find out that what are the different transformations that we have to apply, or what are the different corresponding transformations to the 3D world point that will bring that will give us the world coordinate points, world points as seen by the camera. So, initially I assume again that all the points or the image coordinate system and the camera coordinate system, they are perfectly aligned. Now, after this assumption, what I have to do is, I have to give a displacement to the camera. So, by the vector 0, 0, 1. So, what I will do is, I will bring the camera to a location here. So, this is my camera, where the image plane center is at location 0, 0, 1. So, this is my x axis, this is my y axis, this is the z axis. Now, if I do this transformation, then you find that all the 3D points will be transformed by the vector 0, 0, minus 1 with respect to the camera coordinate system. So, the first transformation matrix which has to be applied to all the points in the 3D coordinate system is given by 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus 1, and then 0, 0, 0, 1. So, this is the first transformation that has to be applied to all the 3D points. Now, after the camera is displaced by the vector 0, 0, 1, the next operation that we have to apply is to pan the camera by an angle 35 degree. I just forgot to mention that in that arrangement the pan was 135 degree, the tilt was also 135 degree. So, after this initial transformation displacement of the camera by vector 0, 0, 1, we have to apply a pan of 135 degree to this camera. So, if I represent that, let us take a two-dimensional view. As we said that panning is nothing but rotation around z axis. So, if I say that this is the x axis, this is the y axis, then by panning we have to make an angle of 135 degree between the x axis of the camera coordinate system. So, the situation will be something like this. So, this is the y axis of the camera coordinate system, this is the x axis of the camera coordinate system, and by pan of 135 degree, we have to rotate the camera imaging plane in such a way that the angle between the x axis of the camera coordinate and the x axis of the 3D world coordinate is 135 degree. And once we do this, here you find that this rotation of the camera is in the anti-clockwise direction. So, the corresponding transformation on the 3D world points will be in the clockwise direction, but by the same angle 135 degree. And the corresponding rotation matrix, which is now given by r theta, will be equal to cosine 135 degree, sine 135 degree, 0, 0, then minus sine 135 degree, cosine 135 degree, 0, 0, then 0, 0, 1, 0, then 0, 0, 0, 1. So, this is the rotation transformation that has to be applied to all the world coordinate points. So, after we apply this r theta, the next operation that we have to perform is to tilt the camera by an angle 135 degree. So, again to have a look at this tilt operation, we take again a two-dimensional view. So, the view will be something like this. So, we take say this as the z axis of the 3D world coordinate system, and in this case it will be the y z plane of the 3D world coordinate system. And by tilt, what we mean is something like this. This is the z axis of the camera coordinate system, and the angle between the z axis of the 3D world coordinate system and the camera coordinate system is again 135 degree. So, this is the angle tilt angle alpha. So, here again you find that the tilt is in the anti-clockwise direction. So, the corresponding transformation in the 3D world point will be rotating the 3D world points by 135 degree in the clockwise direction around the x axis, and the corresponding transformation matrix in this case will be r alpha is equal to 1, 0, 0, 0, 0 cosine 135 degree, sine 135 degree, 0, 0 minus sine 135 degree, cosine 135 degree, 0, 0, 0, 0, 1. So, this is the transformation matrix that has to be applied for the tilt operation. So, after doing this, you find that the 3D world coordinate, the 3D world point for which we want to find out the corresponding image point is given by 1, 1, 0.2. this is the 3D world coordinate point, and after application of all these transformations, the transformed coordinate of this 3D world point, if we write it as x hat, y hat, z hat, and this has to be represented in unified form. So, this will be like this. It has to be r alpha, r theta, then t, and the original world coordinate 1, 1, 0.2 and 1 in the unified form. Now, if I compute this r alpha, r theta and t using the transformation matrix that we have just computed, that we have just derived, you will find that this transformation matrix can be computed as minus 0.707, 0.707, 0, 0, then 0.5, 0.5, 0.707, minus 0.707, then again 0.5, 0.5, minus 0.707, 0.707, then 0, 0, 0, 1. So, this is the overall transformation matrix which takes care of the translation of the image plane, then pan by angle theta and also tilt by angle alpha. So, if I apply this transformation to my original 3D world coordinates, which was 1, 1, 0.2, then 1, then what I get is the coordinates of the point as observed by the camera. So, if you compute this, you will find that this will come in the form 0, 0.43, 1.55 and then 1, again this is in the unified form. So, the corresponding the corresponding Cartesian coordinates will be given by x hat equal to 0, y hat equal to 0.43 and z hat is equal to 1.55. So, these are the coordinates for the same 3D point as seen by the camera. So, now what we have to do is, we have to apply the perspective transformation to this particular points. So, if I apply the perspective transformation and if I assume that the focal length of the camera is 0.035, then we obtain the image coordinates as x equal to lambda x hat divided by lambda minus z hat, which will be in this case of course 0, and y equal to lambda y hat divided by lambda minus z hat, which if you compute, this will come as minus 0.0099. So, these are the image coordinates of the world coordinate point that we have considered. Now, note that the y coordinate in the image plane has come out to be negative. This is obvious because the original 3D world coordinate as obtained by after applying the transformations came out to be positive. So, obviously, in case of image plane there will be an inversion. So, this value of y coordinate will come out to be negative. So, this particular example illustrates the set of transformations that we have to apply followed by the perspective transformation, so that we can get the image point for any arbitrary point in the 3D world. So, with this we complete our discussion on the different transformations and the different imaging models that we have taken. Now, let us try to see the answers to the quiz questions, the questions that we have given in the last class. So, the first question was, what is the concatenated transformation matrix for translation by vector 1 1 followed by rotation by angle 45 degree in 2 dimension. So, here you find that first you have to apply the transformation followed by the rotation. So, the concatenated transformation will be cosine 45 degree sin 45 degree 0 minus sin 45 degree cosine 45 degree 0 0 0 1, then 1 0 1 0 1 1 0 0 1. So, if you multiply these two matrices the concatenated transformation matrix will come out to be 1 over root 2, 1 over root 2, root 2, then minus 1 over root 2, 1 over root 2, 0, then 0, 0, 1. The second question that we asked, that for this square figure whose vertices are at locations 1 1 minus 1 1 minus 1 minus 1 and 1 minus 0, if this figure is first scaled by factor 2 and then translated by factor 2 2, then what is the transformed figure? In this case, the transformed figure will again be a matrix, will again be a square whose coordinates after both these transformations will lie at 0 0, 4 0, 4 4 and 0 4. The third question we had asked is, what will be the figure if the transformations are applied in the reverse manner? So, in this case first you have to apply the translation followed by the scaling, and then after final transformation your coordinates will be 2 2, 6 2, 6 6 and 2 6. Then we had given another problem with vertices of a cube where the scale factors were 2 along x axis, 3 along y axis and z along and 4 along the z axis. So, if we transform this cube with the help of these scale factors, then finally I will get the transformed coordinates like this 0 0 0, 0 0 4, 0 3 0, 0 3 4, 2 0 0, 2 0 4, 2 3 0 and 2 3 4. Then we had given the fifth problem where we had given a 3D world point and the coordinate of the camera. We were to find out what is the corresponding image point. So, here the image point is obtained as x equal to minus 2.63 and y equal to minus 3.68 after applying the transformations that we have discussed. Now, coming to today's quiz questions. The first question is, for a camera with focal length of 0.05, find out the locus of the points which will be imaged at location 0.2 minus 0.3 on the image plane. You assume that the camera and coordinate system and the world coordinate system are perfectly aligned. The second question, a camera with focal length of 0.04 meter is placed at a height of 1 meter and is looking vertically downwards to take image of the xy plane. If the size of the image sensor plate is 4 millimeter by 3 millimeter, find the area on the xy plane that can be imaged. Then the third question, a camera is mounted on a gimbal system that enables the camera to pan and tilt at any arbitrary angle. The gimbal center is placed at location 005 and the camera center is displaced from the gimbal center by 0.2, 0.2, 0.2 in a world coordinate system xyz. Assuming that the camera has a pan of 45 degrees and tilt of 135 degrees, find out the image coordinate of a world point 1, 1.5. Thank you.